Welcome. Hi, my name is Christian Feldman. I'm a encoding engineer at Bitmovin, and recently I had to do with a hypothetical reference decoder a little bit more than I wanted to. And in this presentation, I wanted to share my findings when looking much deeper into this. So first, let's decrypt some acronyms. VBV or HRD. VBV is the video buffer verifier, HRD the hypothetical reference decoder, and for the most of this talk we can just take these as synonyms. They are basically describing the same thing. VBV was first introduced in MPEG 2 and then it was replaced by HRD in H.264a. We see a little bit later, which is a little bit more abstract and a little bit more detailed, but that's basically it. And let's just draw some keywords from this, which we can already use to understand what's going on. So there's something about buffer, something about a decoder, something about verification, and something hypothetical is about this. So this is a hypothetical model which we can use to verify buffering things that are happening in the decoder. So everything that happens on the timeline here, basically. So that's what the HRD is used for. Let's take a very simple encoding model example. In this one, there's 24 frames per second going into the encoder, and then the encoder will output 24 packets per second. And these are, of course, of different sizes. And then we transmit those to the decoder, and the decoder does the opposite thing. It takes the packets, decodes them, and outputs 24 frames per second again, the reconstruction on the other side. What this model, of course, does not take into account is anything that has to do with the transmission, right? Usually transmission is not instantaneous. There's usually some limits on this. And also on the decoder or encoder side, there might be buffering issues. There might be some buffers involved, which might not be big enough to hold certain packets and stuff like that. And all of this is basically ignored here. So what we do now is we extend this model by some buffers, 2 buffers to be precise, one at the encoder side and one at the decoder side. And they are connected through a constant throughput channel. So we have one bucket up here and another bucket down here. And then there's a constant flow of information from the encoder buffer to the decoder buffer. The encoder buffer puts its packet into the encoder buffer, constant flow, and then the decoder takes them out again and does the decoding. And this can be used to model what happens at the what happens for the transmission or what happens for the decoder or encoder buffers. Both of these buffers are linked, and we can basically take a look at either side of this. It doesn't really matter. And so from now forward, we will just take a look at the decoder side, so at the decoder buffer and the decoder, what happens to the decoder buffer, because A, I think this is more intuitive to understand, and B, this is what the standard defines as well. And usually the decoder is also much more restricted when it comes to buffering and transmission and stuff like that. The encoder usually has big buffers, the decoder does not. There's a few parameters which are signaled in the bitstream, which are important here, which we should remember. That's per sequence, there's an initial delay that is signaled. Basically, how long do we wait before we start decoding? And then per frame, we're also signaling some information, a removal delay, so which indicates when a frame is to be removed from the bucket. And we will see an example now. So here's an example. So I went to the local hardware store and got a 4 megabit decoding buffer. And up here you can see a tab, and that is a 200 kilobit tab. And here you can see 5 frames that we're going to decode. And up here is the decoder. And basically what we're going to do now is we're going to open the tab, let the water flow into the decoding buffer, let it fill up a bit. And you can see down here there's an initial delay. So that's basically how long we have to wait until we start decoding, or how long until we start taking out frames from the buffer and decoding them. And that is signaled in the bitstream. And then we're going to decode these 5 frames here. So we're going to start with the first I frame, of course, and then there's a P and 2 more B, and then a P frame. And here we go. So we take the bytes out for the frame from the decoding buffer, pour it into the decoder, and the decoder will instantaneously decode this and give us an output frame. That's the hypothetical idea. And yeah, we're decoding here at 0.2 frames per second. So every 5 seconds, we're decoding 1 frame, taking it out of the buffer, pouring it into the decoder. And that's basically how the hypothetical reference decoder model works, if everything is okay. We can also put this into the form of a graph. So on the timeline here, we have the time. On the other axis, we have the buffer fill, and there's a maximum buffer fill that we can have. And we can see the same thing here. So we're filling up the buffer, and then after the initial delay, we're removing the frames, it's all instantaneous. Meanwhile, the buffer always fills up because we have a constant flow into the buffer. That's it. We can also put this into a little bit of pseudo C++ code here. So per frame, we're calculating some values. We have a removal time that we can just get from the bitstream, right? It's a regular grid, so you can just calculate these times. The size we can just read from the bitstream. We just count bits, then we have the size. And for each of the frames, we calculate a start and an end time, which is the time when we start the transmission of the first byte of this frame and the end time when we finish transmission of everything. And how these are calculated is pretty easy. For the first frame, the start time is 0. And then for each following frame, the start time is just the end time of the previous frame. So every time we finish transmission of a frame, we immediately start the transmission of the next one. And then for the end time, we can just calculate that from the start time and from the size and the HRD bitrate, right? We can just say how long, what's the size divided by the bitrate, and then we know how long it will take to transmit all of the bytes using that HRD bitrate. And then the assertion that we have to do is, one of the assertions that we do is, for each frame, we have to make sure, in order for this to validate, we have to make sure that frames are only removed after all of the bytes have been transmitted. So the removal time has to be greater than the end time. Something practical that I also wanted to show is how the HRD looks for a real file. So this is YuView project that I have been maintaining. It's open source. You can just go to GitHub and check it out there. And I just used FFmpeg to encode a file into a certain format. And here we can see it. So this is, you might recognize this is the Sintel sequence. And now we can go to the Bitstream tab and take a look at all of the packets that are in the bitstream. And what we can see is that we have the signaling here, which I mentioned before. So per sequence, we have the signaling of a buffering period information. So this is the initial CBP removal delay. This is the how long do we have to wait until we start the decoding. And then per frame, we have peak timing information, which gives us information about when a frame is to be removed relative to that start time from the decoding buffer. And then we can also take a look at the bit rates, and then we can see what I already mentioned, that the first I frame, of course, is the biggest frame, and then the following P and B frames are of various sizes, but they are all very different in size. And then we can also take a look at the corresponding HRD model. So this is exactly the same plot, just for a real sequence, and we can see that this is the initial removal delay where the buffer fills up, and then at some point we start decoding, and then we can see where frames are removed from the buffer and where how the buffer fills up. And then also YuView will tell you all of the different times that I've been talking about. So transmission start, transmission end, when what frame is transmitted and when the frame is removed, and all of that. And of course, something can go wrong here if we're not looking out and something is not correct. Things can go wrong. So the first situation, what I want to show here is a buffer underflow. We can already see one of the main differences here is that we have an iframe that the following frames are pretty big, right? So we have the same iframe, then we have a p frame, another p frame which is pretty big, and then one very big iframe. So we're starting decoding. First iframe works, and then the decoding buffer is already, you can see it's not very full, so that's always an indication. Then we're decoding the p frame, that works, and now at the next point we're trying to decode the last iframe, and unfortunately there's not enough bits in the decoding buffer, so it fails. And then we have a violation. So in this case, the end time of the transmission would be after we try to remove the frame from the buffer, and it doesn't work. The other case is, of course, a buffer overflow. So in this case, you can already see that the frames we're trying to decode are much smaller. So we again start with an iframe, and then we're decoding a set of frames which are much smaller than the other frames were. So there's a P frame, and then we're decoding a small B frame, another B frame, and you can see the buffer filling up slowly. There's another P frame, and we're removing data from the decoding buffer slower than it actually fills up, and then at some point we have an overflow. We weren't fast enough to remove data from the decoding buffer, and then it overflows. We can also put this in a graph, so this is what it looks like, and one thing you might think of is, but wait, why would the buffer overflow? Can't we just turn off the tab? And yeah, exactly, that's what we can do. So this is what's plotted here. So basically, once we reach this limit, we can just turn off the tab, and then once we remove frames again, then we can turn it on again, then off again, and that way we can make sure that the buffer never overflows. This is also called VBR mode, so variable bitrate mode, and this is part of the HRD as well, so it can't really overflow. Usually that's not a problem. You can just say, we have a fixed channel, we can just transmit less bytes than can go through the channel. That should never be a problem. There's another mode that the HRD can be operated in, which is CBR mode, constant bitrate mode. And in that mode, the difference is basically that the tab cannot be turned off. It must never be turned off. So the flow into the buffer is always constant and it's always on, and the end times are always the start times of the previous frame. How do you achieve this? Well, either the encoder could reduce the increase the quality or the bitrate of the frames in order to always take out enough data from the buffer. Or if that's not an option, or it doesn't really work because the sequence is pretty easy to encode, then you can add filler data. And that is usually what happens. So most encoders do not influence the rate control if it's a CBR encode. They just add filler data in order to not make the buffer overflow, and that's it. That's the difference between VBR and CBR. On profiles and levels, or more levels in this case. As you might know, a level is a set of restrictions that you can set for a decoder in order to define how much a decoder can do physically. That's very important for hardware decoders specifically, because they are limited by what their hardware can actually do. And this is H.264 and some of the values are quite easy to set and to check, which is the number of macro blocks you can process per second, the maximum frame size that the decoder can process, or also the maximum number of decoder picture buffers that you have. It's just in megabytes. And two more values which are defined here in the level limits are the max video bitrate and the max CPB size, so the coded picture buffer size. And those are exactly the values that I just talked about. Those are the buffer rate, the HRD buffer rate, and the maximum size of the HRD buffer. Those are these values. So my main point here is, if you get a bitstream and somebody says, please verify if this adheres to a certain level, you can easily check the other values. But in order to check the bit rates, so just by looking at the bit rate of the file, just by looking at the file size and the duration of the file, you will not be able to verify this. So you need to check the buffer models in order to make sure that this really adheres to a level. And also the other way around, so this is hypothetical, a pseudo FFmpeg call for an encode. So let's say we set a level here and then get an output. It depends on what your codec does, but it could happen that it actually just checks the resolution and the buffer sizes, but not the HRD parameters for this, and that it does not automatically set this. So depending on the codec that you're using here, you might actually want to also set the buff size in order to make really sure that your level limits are kept. Short segments. In short segments, everything is a little bit different, and that is also where bitrate is not really bitrate, or where you have to really look out what bitrate is and what you mean. So let's say you have a long encode, 1 hour, and then you just divide the length or the file size by the duration, and then you have a bitrate. That bitrate cannot be bigger than the HRD bitrate that you're setting, right? Imagine the scenario I showed. You open up the tab, and then over a long period of time, you can never take out more bits than is flowing into the bucket. That doesn't work, and that is also true. But for short segments, this looks a little bit different. And let's say this is just a scenario here for parameters. So let's say we have a buff size of 2 megabits, and we have a bitrate of 1 megabit, and then we are just encoding one frame, just one single frame, and that one single frame has 1.5 mbit. So does this work with the HRD model? Well, let's just say we have we're filling up the buffer to a certain degree, and this is the 2 megabit limit up here, and then we're filling it up to some point, and let's say this is, I don't know, 1.8 megabit, so the init delay is long enough so that it's filled up to 1.8 megabit, yeah, then certainly we can take out 1.5 megabits out of the buffer if it's full enough, right? So if the buffer is full enough, then we can definitely take out 1.5 megabits out of that buffer. But let's calculate the bitrate here. And by bitrate for this, I mean the sum overall of the frame sizes divided by the duration. And let's say this is 24 frames per second, then you will end up at 36 megabit for this one frame if you just divide it by the duration that it is shown. And these are things which are not really going together, right? So this works, but you have a buff size. You have a buff size of 2 megabits, but you're taking out 36 megabit for one frame. It somehow, so the bitrate here is not really the real bitrate that you're getting. And if you're thinking about the hypothetical FFmpeg call here again, you might actually be wanting to do something like this for this very, very short segment. The target bitrate that you want to achieve for this one frame is 36 megabit, but the max rate and the buff size are limited by these values. And that is possible, as you've seen up here, right? So that can be done. And it depends a little bit on your codec, how he handles it. Be sure what happens. This can go wrong. And yeah, we've seen that go wrong. One final thing, one other thing that the HRD also is able to verify is decoding and encoding. So as you might know, the decoder, of course, decodes frames not in the order that they will be displayed. And there's two things running at the same time here at the decoder. There's one decoding process which decodes the frames and puts them into the decoding picture buffers in the order that he decodes them in. And then there's an output process that outputs the frames in the display order to some device usually. And these two are, of course, synced. But there's a certain situations that you have to avoid, of course, that must never happen. So the decoder must never override a frame which hasn't been output yet, a frame buffer that hasn't been output yet. And the output process, of course, also must never output a frame which hasn't been decoded yet, because that, of course, also doesn't work. And this is another verification thing. So there's additional metadata that is signaled in the bitstream in order to check this model too. Finally, I want to go to some question-answer style of things that we've heard and observed and what happens in reality. So how does this apply for segmented streaming? Does this apply at all? Well, mostly no, because of course for the transmission side, it doesn't really apply, right? For adaptive streaming solutions, we don't have a fixed channel. We don't have, we have the internet. We get what we get. That might be anything. And so for the transmission side, mostly no. And also for the decoder side. In adaptive streaming, we're downloading whole segments usually. And so they are downloaded when we start the decoding process typically. So the decoding buffers in the decoders are very big. And so you don't have buffering issues there. And also for the decoders, for the actual decoders, if you're thinking about the level limits that I talked about, most decoders are very tolerant to these and if they change a little bit. Another thing, I use HRD VBV parameters to limit the bitrate peaks. That is something we've seen often being done, so that you try to influence the rate control by setting the HRD parameters. And this works. So for example, you can do a CRF encode and set HRD parameters to cut off like the higher bitrate peaks, like a cheap man's per title encoding. That works. And you can also influence the rate control a little bit differently by setting these parameters. It will typically give an upper limit on how high the bitrate can get. My question then is, but why though? Why are you doing this? Are you just doing this to influence the rate control into your favor? Then maybe there's other parameters that you should rather look at in the encoder in order to do the same thing. Those might be better suited for your needs, like a stricter bitrate mode maybe, or 2-pass encoding, or 3-pass, or something like that. Some other sort of rate control fix or modification that might help you better. Because you always have to consider the HRD model, if you set those in the encoder, they are a hard limit for the encoder to keep. And if the buffer is about to run low, then the encoder will forcefully try to keep it full, that there's no underrun. So it will drop the quality to very bad levels if that happens. And that might not be what you're looking for in certain situations. But it can smoothen the rate control, but it's a bit hacky. So I would like to formulate this a little bit differently, where it would be I use the HRD VVV to counteract sudden quality drops because of the rate control goes out of control. That's something that that also can help. So if the rate control, if for certain content and short segments, the rate control does something that you're not expecting or that you don't want, then the HRD parameters might actually help to smoothen that out a little bit. But again, it's hacky, and maybe using some other methods might be more effective, like checking the other parameters, that other vectors that you have to influence the rate control a little bit. I use CBR to get a smoother bitrate distribution. Just don't. As I said, CBR is just adding filler data to the whole thing. That's about it. Usually the encoders don't have any other change in the control if you have CBR mode. So what you get is a bigger bit stream, and that's it, with filler data in it. If you don't have a very, very, very strong reason to use CBR, like a very legacy device that needs it, or legacy muxing or transmission scheme that really, really needs it, don't. That's it. So with that, thanks, and time for questions.